keeping you on.
They're recorded. I value education.
Good answer. Yeah, home stretch, we've got 2 more class meetings and then the final. So our final is on Tuesday the 10th, so next week. You want to make sure you're getting your homework and quizzes done. You are allowed a no card, a 3" by 5" no card front and back on the final. You can have definitions, theorems, formulas, but you cannot have anything from chapter 5 or 6 on there because we haven't tested over that. You cannot have any worked examples. So like you can have generic formulas for derivatives, let's say. You could have like the derivative of b to the x is b to the x ln b. But you can't have something specific like the derivative of 2 to the x is 2 to the x ln 2. So it's kind of a fine line between the difference of the two, but you cannot have these specific worked examples or specific type formulas on that no card. Okay, you'll need to turn them in with the final, just so make sure everything's on the up and up. If you have any other questions about that, please let me know. There's a final exam content sheet that has been uploaded here too, under exam reviews and the final exam review. So the content for the final, you can start, going over old material if you need to. That's there as well. Okay. So do y'all have any homework questions? Yeah.
5.1 number 12.
Let me put that in there. So we have to, for the given value of n equals 40, use sigma notation to write the left, right, and midpoint Riemann sums, then evaluate each using a summation calculator. And then based on the approximation found in part A, the approximations found in part A, estimate the area of the region. So, okay, that's quite a lengthy, maybe not terribly lengthy, but for the left, right, and midpoint Riemann sums, what's the difference between those three as far as the formula for the Riemann sum goes? Well, we're going to 40, so we'll go ahead and fill that in. So that's our Riemann sum, regardless of which one we're using. So as we go through the left, the right, and the midpoint Riemann sum, what changes in that definition?
X star k.
Yeah, the x star sub k. Right, so the x star, the thing we evaluate, the thing that tells us each rectangle's height, is different for the left, right, and midpoint. So for the left, so our x star sub k. For the left, Riemann sum is defined how?
Is it k minus 1 delta x?
Yeah, close. Remember we had that a, but
Oh, a plus, yeah.
a plus k minus 1 delta x. For the right, you really don't need to commit to memory the left and the midpoint. It's the right one that we use when we're evaluating those things exactly. So what was the right x star sub k?
K
A
delta x.
plus, A
Yeah.
plus K delta X.
Yeah,
A plus k delta x. And the midpoint,
A plus K minus 1/2 delta X.
yeah, a plus k minus a half times delta x. So those are the only things that change. The formula we wrote up there in blue will be the same for all three, with the x stars changing. So our function is the square root of x from 0 to 24, with n equal to 40. So maybe we can look at one of these. Was there a specific part of this that was giving you trouble,
Not
or
really.
just
I
didn't really know where to start?
saw the big symbols and kind of got confused.
Okay, all right. So we're using this blue definition with, of course, f of x being the square root of x. So we can just look at one of them. Is there any one in particular I want to look at, the left, right, or the midpoint? So since we wrote the left down first, we'll just work with the left. So all they want us to do is write the sum out in sigma notation and then evaluate the sum using a calculator. So we're just going to evaluate the sum from k equals 1 to n, to 40 rather. F evaluated at x star for the left Riemann sum, again, is a plus k minus 1 times delta x times delta x. So we'll fill in, what would our a be for this?
0.
Yeah, we know that because the interval we're given is from 0 to 24. Okay, so that's, we'll just write it, I'm gonna write it below here. That's f of 0 plus k minus 1. It's gonna say k minus 1, but we also need to find out what this delta x is. Because it's, not only does that go into the function, but then we multiply all of that by delta x. So what would delta x be? Is what?
3/5.
3/5
Is it 24 over 40?
b minus a
Oh,
over n.
yeah.
Yeah, 24 minus 0 over 40. What is that? 12 over 20. 6 over 10. 3 over 5. Yeah. So that's our delta x. Okay, so let's write out the sum. We're summing from 1 to 40. We've got to take f and evaluate it at k minus 1 times 3/5. And then we're multiplying by all of that by 3/5. So really the only other step we need before we just put this into a calculator is to evaluate k minus 1 times 3/5 in the square root function. So we're just going to put that into the square root. Now you can leave it like this or expand what we have here if you want. But since we're going to put it into a calculator, I don't think it matters. So that's what we're computing. That's going to give us, using left Riemann sums, or the left endpoints, with 40 rectangles, is going to give us an approximation of that area. Does anyone have any questions on that?
Why is it times 3/5 twice?
Well, the delta x is present in the x star, and it's present outside of the function itself. So you have that delta x showing up twice. We just go back up to the definition. I don't know what that's doing. So the x star for all three of these involves a delta x, but that delta x, this delta x here is the width of each rectangle.
Okay.
Yeah. Any other questions? Yep. All right. So then what they want you to do is compute the other two the same way. Throw that into a calculator and then look at the three values for part B, the three values that come out from the left, right, and the midpoint, and use those to give your best guess as to what the actual area might be.
If you were to do a delta x squared in the original equation and calculate it that way, would it come out the same?
A delta x squared where?
Like in that original equation.
This one?
Yeah. Since you have the delta x twice, if you were to like distribute that outer delta x into the parentheses being whichever, your left, right, or middle Riemann sum.
Yeah.
If you were to just do like a delta x squared, multiply it by itself,
It wouldn't work.
It wouldn't work.
It wouldn't work because this delta x is kind of by itself, but the delta x that's with this x star has to be put into the function first.
Oh, okay.
So depending on what the function is, I mean, you could force that delta x into the f of x star, but it depends on the function. Like for this function, we would have to square it to put it in the square root. But if that were like a sine function, we would have to inverse sine it to put it in there. So yeah, they're two separate things. So those delta x will be there twice. Remember, if you're using Desmos, it has it in terms of n. You might be able to change that, but so we're going to do the square root of 3/5 times n minus 1, and then we're going to multiply all of that by 3/5. So we would take that to be our approximate area there. For this one. And again, the only thing that's going to be different for the right and the midpoint is that thing right there, or this thing right here under the square root. Is that clear? Do you have any other questions on that? If that doesn't help that much, just let me know, and we'll go through the other ones. You're welcome. All right. Any other homework questions? So remember, these types of approximations aren't going to be on the final. The only thing as far as Riemann sums are concerned, you should know what's happening when we use Riemann sums for an approximation, but they won't show up as an approximation on the final. The way they'll show up on the final, it says you use the definition to evaluate the integral from 2 to 3 of x squared minus 1. So that's where we have to look at the limit as n approaches infinity on our Riemann sum, right? So like one of those will be on the final, but as far as approximations, they won't be.
We're just rewriting it in summation down to the limit.
Yeah, and then we had, for evaluating these, we had that theorem, like 5.1, part 2, that made these computations pretty easy. Okay then, so we'll finish 5.3. We are a little behind.
Is that final cumulative?
Yeah, so some old stuff will be on the final and some new stuff.
Okay.
And we left off with the fundamental theorem of calculus here in 5.3. This here, and that it tells us, a shortcut method to bypass the limit of the sum or computing an infinite sum. We compute a definite integral this way, So what we had to do was first find an antiderivative of lowercase f of x. We called it uppercase f. And then once we find the antiderivative, we evaluate it at the upper bound of our definite integral first. So we plug that number into the antiderivative, and then we subtract off the lower bound plugged into the antiderivative. And we're using a shorthand notation that we have here in the box, capital F, evaluated at B and A. And then we did compute a couple of these. Yeah. We did compute a couple of these using the theorem itself.
Can you scroll back up real quick?
Mhm.
Just a little bit. Thanks.
So as far as example 1 and 2 goes, does anyone have any questions or need a refresher on what we did there? Okay. So then example 3 is the integral from 0 to 2 pi of 3 sine x dx. And just as a reminder here, when we compute these definite integrals, at least the context for now for us is we're saying, okay, well the function 3 sine x, what does that look like? And then we're finding the area that's bound by the function and the x-axis. So we're finding this area and this area. In other words, definite integrals give us a net area. So that's just there for reference. So we first find the antiderivative of 3 sine x. So what's the antiderivative of 3 sine x?
It's 3 cosine.
What do y'all think? 3 cosine? Let's check. Is the derivative of 3 cosine 3 sine?
Would it be negative 3
Negative
cosine?
Negative 3 cosine.
Right. Because the derivative of 3 cosine is negative 3 sine, and that's not what we have. We have positive 3 sine. So the antiderivative of sine is negative cosine. The 3, you could pull that out as a constant. Okay, so we have negative 3 cosine x evaluated from 0 to 2 pi. So the negative 3 is just multiplying all of it. Some people choose to just work with what they have here and say that it's negative 3 cosine of 2 pi. So there's our capital F of B, our antiderivative at the upper limit. And then we have to subtract off, that's just in the formula, that one right there. We have to subtract off the antiderivative evaluated at the lower limit. And so what do we get for that result?
0.
0, yeah, because cosine of 2 pi is cosine of 2 pi is 1 times negative 3 is negative 3 minus cosine of 0 is also 1 times negative 3. So we have negative 3 minus negative 3, which is 0. So the net area there is 0. We can see there's equal contributions above and below. And maybe looking at it visually is not, it's I don't think it's enough to say that, okay, the area above and below are exactly the same. I don't think that's 100% clear from the graph itself. But what we're saying is, through this work, we know that this area above and below are exactly the same. Other people choose to, or we could evaluate it this way, other people choose to leave the constant out and then just evaluate cosine of x from 0 to 2 pi. Figure out what that is and then multiply everything by -3. Because the 0 and the 2 pi are only getting plugged in for x. You can see it's the same result. We have cosine of 2 pi minus cosine of 0. That one. And so we have -3 times the quantity, 1 minus 1. So it doesn't matter if you leave the constant in both computations or leave it out and multiply it in later. I would just say whichever ones makes most sense to you, do that. I just think the more constants you have in there, and you're subtracting things and you're adding things or whatever, the more opportunity there is to miss a sign or something. But it's totally up to you. Okay, so that net area is 0. Do y'all have any questions on that? And honestly, I think at this point, you should know all of those antiderivatives from 4.9. And if you don't, I would just make no cards for them. Because we're kind of, for the most part, we're out of derivatives with Chapter 5 stuff. Okay, how about example 4? So the first question is really, can we integrate or find the antiderivative of a quotient? At this point, no, unless it's a known quotient. So products, remember, products and quotients, you cannot, quote unquote, distribute the antiderivative across. So please do not ever do this and say this is the antiderivative of this divided by the antiderivative of this, or another variation of that. That will never be true. So what do we need to do here?
You can separate it though, right?
Yeah, we
Like
can.
the square root x over x.
Right. So we've got two things in the numerator over a single thing in the denominator. We want to actually simplify that function before we take the antiderivative. So we'll go, just so we don't run out of space, go up here. We're going to write square root of x over x minus 1 over x and simplify. So the square root of x over x turns into what? Yeah, 1 over the square root of x, or x to the negative 1/2. Just subtracting the powers, 1/2 minus 1. Do we want to write the 1 over x as x to the negative 1?
Sure.
Okay, some said no, some said yes. So once we've split this up and simplified it, it's now just a power rule on both of those, or maybe it's not, we'll see. What happens when we try the power rule on x to the negative 1? You have to add 1 to the power and then divide by that same result.
Sure.
Yeah, so you can't do that. And x to the negative 1 is the only exception to the power rule. So whenever you see x to the negative 1, you want to leave it as 1 over x, I think is more recognizable as far as the antiderivative goes. So we're going to split this up into two different antiderivatives. Yeah, I guess you don't necessarily have to do that. So what is the antiderivative of x to the negative 1/2?
It's just x to the 1/2.
X to the 1/2?
Am I going backwards with you?
Yeah. Divided by 1/2, right? So we add one to the power, and then we divide by the same result. So it's x to the 1/2 over 1/2. What's the antiderivative of 1 over x? Natural log of x. So that one's the natural log. Technically, we should use the absolute value. That is the antiderivative of 1 over x.
Would you want to simplify that fraction?
Yeah.
Just say 2 square root of x.
Yeah, I would do that. And both of them are evaluated from 1 to 4. So we'll just rewrite this. 2x to the 1/2 minus the natural log of x. Why is it okay to drop the absolute value here?
Because we're working with all positive numbers.
Right, because we're on the interval 1 to 4 rather, and the interval from 1 to 4, the natural log is always positive. So there really isn't a need for the absolute value in this particular example. Okay. Does anyone have any questions? Let's see if we can fit this in. And so we're going to just evaluate the entire antiderivative at 4. So there's the antiderivative evaluated at 4, and then we have to subtract off the antiderivative, if I can put this in here, the antiderivative evaluated at 1. Is everyone okay with that? When you have to subtract off that f of a, you have to subtract off all of it, not just the first thing or the second thing. So we have the 2 times the square root of 4, 2 times 2, minus the ln of 4. And we'll just leave our answers exact. We have minus 2 plus ln of 1 or plus 0. So we have 4 minus 2, we'll combine those. 4 minus 2 minus ln 4. And so that's our exact area. Is this making sense? Does anyone have any questions, comments, or concerns? So at least we don't have to compute the infinite sum anymore. I don't know if it's, it's a little bit better because we know antiderivatives, but with a lot of them, it's still kind of a lengthy process. Again, with derivatives, what we had was a clear-cut way to take a derivative. It says if your derivative consists of a quotient, you just do this, right? But with antiderivatives, it's not as straightforward. We can check our results as far as the antiderivative goes, but the process of finding antiderivatives in general is more difficult than finding derivatives, for sure. But case in point, example 5, what would that be? What would we do there? What'd you say, Alex?
Oh, I was asking myself if that's inverse sine.
Yeah, is that inverse sine? definitely is. And so like specifically with the inverse sine and the inverse tangent antiderivatives, if you don't remember those, you're just going to be staring at that thing forever, wondering what you could possibly do to find the antiderivative. And there's nothing you can do. If you don't know that it's, at least for us now, there's nothing we can do. If you don't know that those are inverse sine or inverse tangent, that's it, you're done. So let's see how much. We'll write those here at the bottom because they are extremely important. But you just have to remember that the antiderivative of 1 over root 1 minus x squared is inverse sine. Evaluated from 0 to 1/2. Right, maybe we can write it here. We've got enough room. The more generic one was the antiderivative of 1 over the square root of a squared minus x squared. What is the antiderivative of that? Inverse sine of, it's got to involve an x. X over a, yeah. So definitely worth remembering that. Okay, so we apply the fundamental theorem of calculus in evaluating inverse sine at 1/2 minus the inverse sine, excuse me, of 0. So what's the inverse sine of 1/2? In other words, the sine of what angle gives me 1/2?
Pi over 6.
Pi over 6, right. Inverse sine of 0. The sine of what angle gives me 0?
0.
0. Yeah. Pi over 6 minus 0. Do y'all have any questions? Okay, how about the antiderivative of cosine 2x? Sine 2x over 2, what do y'all think? Does everyone agree? What's the derivative of the sine of 2x? Derivative of sine is cosine 2x by the chain rule, cosine 2x times 2. So the derivative of the top is cosine 2x, and then we have divided by 2, just gives us cosine 2x. So again, if you take the derivative of your antiderivative, the derivative of this thing should be this thing right here.
So if you were to do the bottom times the derivative of the top,
It'd still work.
etc., you would get cosine 2x,
Yeah,
right?
after you simplified it.
Okay.
Yep.
Okay.
Evaluated from 0 to pi over 4. And so honestly, I would personally write it as 1/2 times that, but it's totally up to you. So I think the big thing here is being able to find the antiderivative. The next thing is being able to successfully apply the second part of the fundamental theorem in how you evaluate. So we have 1/2, then we have the sine of 2x evaluated at pi over 4. Or sorry, sine of 2x. So sine of 2 times pi over 4 minus sine of 0, or 2 times 0. So we have sine of pi over 2 minus the sine of 0. 1/2 times 1 minus 0. And so again, the 1/2 represents the net area on the cosine of 2x graph from 0 to pi over 4. Any questions on that?
Do you have to separate the 1/2?
No, we could have just evaluated it at this step right here,
Okay.
and had both of these. The only difference is we wouldn't have the half there, but we would
Okay.
have both of those over 2.
Okay, so it's not.
Yeah, it's not crucial that you do that. Any other questions? Okay, how about 10e to the 2x? What's the antiderivative of 10e to the 2x? Five e to the 2x, do y'all agree? I guess there's a couple of ways to look at it if you're going to pull the 10 out. Or you could just leave it in. So the antiderivative of e to the ax is e to the ax over a. So 5e to the 2x is the antiderivative evaluated from 1, or sorry, 0 to 1 rather. Okay. So either leave the 5 in with it, or you could take the 5 out. The 0 and the 1 are just going in for this x here. So there's f of b minus f of a. So we have 5e squared. E to the 0 is 1. 5e squared minus 5. The only difference if you left the 5 out and just evaluated the 0 and 1 on e to the 2x, your answer just would have been 5 times e squared minus 1 instead. So I think either one is fine. All right, any questions on this stuff? Antiderivatives aside, those actually showed up in 4.9, so again, know those formulas from 4.9 for sure. Everyone feel okay with this? Okay. So what's wrong with the following calculation?
Second step.
This step right here?
Yeah.
What's wrong with that one?
It's, I feel like it's not correct. Just in general, it's not. I don't know exactly what that person did wrong, but I don't think it's, because it would be, you would find the antiderivative of the 1 over x squared.
Okay, so yeah, we're gonna look at the antiderivative of 1 over x squared.
Would not be x to the minus 1 minus 1.
All right, let's check that step. What's antiderivative of x to the negative 2? We're going to add 1 to the power and then divide by that power. Evaluated from negative 1 to 3. That looks all right.
Yeah, that's it's the next step.
The next step, so notice x to the negative 1 times negative 1 is really just 1 over x times negative 1. So that's, I think that second step could be seen as we're just going to reciprocate that. And since it's divided by negative 1, we're just going to write it like that. Is that all right? Seems okay. Nothing wrong with rewriting that algebraically. We'll plug the 3 in for the x, so we have a minus 1/3. Minus 1/3. Subtract off the function evaluated at negative 1. So we have this minus from the fundamental theorem. And when we plug a negative 1 in here, we get a positive 1. We have a minus 1/3 minus 1. Does that seem all right? Yep. And negative 1/3 minus 1 is negative 4/3.
So nothing.
So nothing, or let's go back. So everybody read that again.
Continuous aspect.
Yeah, if this function has to be continuous on this interval.
It's not
Right.
defined at zero.
So where is our function not continuous at? 0, and we're passing through 0 like it's no problem. So that's what's wrong with the computation.
So is it just essentially the computation can't actually be made? Let me rephrase that. You can't use that theorem to solve
Yeah,
that.
kind of, yeah.
In that sense.
You can use it, and if you go on to Calc 2, you'll see how to use it. It's virtually the same, except for you've got to use limits. But yeah, we can still use our techniques, we just have to modify them a little bit. Because what happens when this function is, what happens at 0 and 1 over x squared?
Yep, 1 over squared.
Okay, so is it an asymptote or is it a whole? It's an asymptote. So it's saying, like, you know, if you looked at the function, and maybe we can draw it out too. Let me finish this. F of x, 1 over x squared is not continuous on the interval negative 1 to 3. So that's our answer. But our function 1 over x squared is doing this. So what we're trying to ask is, so what is this area from here to here, and this area from here to here? I mean, it might be infinite, but sometimes those things are finite, which is really weird. Because if the thing goes off to infinity, how could it possibly ever be a finite area? Guess you'll just have to stay tuned to the next class to see how that works. But that's essentially what we're trying to answer with this right here. So, yeah, I mean, with limits and infinity, you get a lot of paradoxes, because there's a paradox inherently built into the notion of infinity, right? Okay, so, I'm not going to be like tricky like that on the final, but you should be fully aware of what we're trying to do. And just an algebraic approach to this function, saying, hey, wait a minute, I'm trying to find this area that's next to a vertical asymptote. Okay. So the last page is just kind of connecting the dots between the first part of the fundamental theorem and the second part of the fundamental theorem of calculus. So in part one, we were taking the derivative of the area function. That's what that represents, the derivative of that integral. That integral is the area function. So that says that if f is integrated, then differentiated, or vice versa, you arrive back at the original function. We also know that in part two, the integral of some function from a to b is the antiderivative at b minus the antiderivative at a. But they're going to rewrite this a little bit differently and say that lowercase f that was present originally was just the antiderivative. And in other words, the derivative of capital F is lowercase f. So this is the same thing as lowercase f. So you know, like, that might make sense when we talk about like position, velocity, and acceleration. Remember we said that if we take the antiderivative of velocity, the antiderivative of velocity gives us what?
Speed?
Huh?
Is it about the speed?
No, acceleration. Or no, no,
Acceleration
position,
is the-
excuse me.
Yeah.
Position, right?
Position. If you integrate velocity, you get
Or
position.
S of t, that's what I had. For some reason, S means speed.
Right?
Yeah.
Antiderivative of velocity is position evaluated from A to B. Evaluate it this way. But if we looked at the velocity on AB, this is our velocity function. But when we look at the antiderivative of that from A to B, we're actually computing this. What does this computation give us? If
Well,
I
if
look at
it's-
the position
it gives
at
you
B
the-
minus the position at A, what would that tell me?
It gives you the total displacement.
Yeah, that gives you the displacement. The change in position, right? From A to B, how much did the position change from A to B? So that's like the net area, right? If I start here, walk over to the podium, and then walk back to where I started, you know, it's kind of like a graph that's like this. You've got the same area above and the same area below. That displacement is zero. If I start here, walk over there, then here, so my total change in position is zero. Because you've got a net area of zero. This is me walking over to the podium, and this is me walking in the opposite direction. But if we think about velocity, we know that the derivative of the position function is the velocity function, right? Instead of saying the integral of v of t, I can say the integral of s prime of t is equal to this right here from A to B. So that's really all this is showing, this part right here. You know, you can think of it specifically with like an example like this. So taken together, those two parts, the differentiation and integration, are inverse processes, i.e. each undoes what the other one did. And then I just took this quote from another calc textbook. We kind of take these two theorems for granted, but I mean, it really was, as this person says, the most important theorem in calculus, and indeed ranks as one of the greatest accomplishments of the human mind, is this guy's opinion. But he's a well-known calc author, so the theorem is like a really big deal, even though we just kind of use it and not really think about what it is. Okay, so I do want to go back to kind of putting both of those together and seeing that they are actually the same thing. And so let's look at the derivative with respect to x of the integral from 1 to x on t squared minus 1 dt. So we evaluated something like that using the first part of the fundamental theorem, and it might have been a while, but does anybody know what this would turn out to be? So if we go back to the first part of the fundamental theorem, this part right here, Right, because I'm taking the derivative with respect to x from 1 to x on t squared minus 1. What should that turn into?
X squared minus 1.
Just x squared minus 1. So this should, or this is rather, just x squared minus 1 by the fundamental theorem of calculus, part 1. But we could also now use the second part of the fundamental theorem and say, in order to evaluate this, it's a little bit longer of a process. But in order to evaluate this, let us first take the antiderivative of t squared minus 1, evaluate it from 1 to x, and then we'll apply, or then we'll take the derivative of all of that. So the derivative is the thing we're going to apply last here. What's the antiderivative of t squared minus 1 with respect to t?
T cubed over 3 minus t.
Right. T cubed over 3 minus t. And we have to evaluate that from 1 to x. Remember, these bounds from 1 to x are applied to the dt, the t squared minus 1. So these are values for t. The lower bound is when t equals 1, and the upper bound is when t equals to x. So in for t, we're putting x first, and then we're going to plug in 1. We still have the derivative of that we'll do later. So first in for t is the upper bound, x. So we have x cubed over 3 minus x. That's f of b. And we subtract off f of a. So that's actually from the second part of the fundamental theorem of calculus that we're able to evaluate that. So we've evaluated the integral from 1 to x. We've got this expression. What happens when we take the derivative of what we have inside the brackets? What's the derivative of x cubed over 3?
Lowercase f of x is what you get, right?
Yeah. So the derivative of x cubed over 3 is 3x squared over 3 minus the derivative of x minus the derivative of what is this stuff? Just 0, it's a constant. The same result we had from the first part of the fundamental theorem. So this derivative is going here and here. So I don't know if that's miraculous or not, but it does. If you forget that first part of the fundamental theorem, it's a little more difficult, but you know, in theory, if you forgot it, you could still go through this second process to get what that result should be. Anyone have any questions on either of those? Just showing that with a specific example, the first part of the fundamental theorem works out how it should work out. We really didn't have a chance or opportunity to prove that, but at least with specific examples, we can show that it is true. So just a reminder, when we look at derivatives, the units for taking a derivative are what? What do we get as units there for a derivative?
Displacement over time.
Yeah, so like specifically, if we have y and x, if we take the derivative of this function f of x, what would the units be? I don't have specific units, so you can't say something specific.
Would it be,
But what do we do with the y and the x? If there's units associated with y and x, what do we do when we find a derivative?
isn't the x unit squared?
Not the x unit squared.
What is,
Derivative.
I don't know what's going on anymore. Oh, turkey head.
Well, okay.
It'd just be x. It'd just be whatever the units on x are.
Let's say hours. Y is measured in miles. If I take the derivative of that function,
You get
it's y over x, right? Because the derivative is a small change in y divided by a small change in x. So the units for the derivative are always the units of y divided by the units of x, whatever they may be. I mean, more specifically, it's the units of the dependent variable divided by the units of the independent variable.
Because we're finding the slope.
Yeah, right. Right. So I'm just going to erase miles an hour, but when we find an antiderivative or a definite integral, what are the units?
That's the square. I don't know what area it is. Units of area.
So with the definite integral, notice what we have here. Here's our y. Here's our x.
So it's
Y times x?
Units of y times the units of x, right? And again, if we think of something specific here, if we think of like f of x as a velocity function, where velocity is measuring miles per hour, right? The y is the velocity, so it measures in miles per hour, but time is in hours. When we look at the antiderivative of velocity, what do we get? Position. So miles per hour times hours, the hours cancel out and you just get miles for position. You know, this, we don't see a whole lot of applications, but when you do apply derivatives or integrals or definite integrals to a physical application, that's how we determine the units. I think it's it. Yeah, we don't necessarily need to know this, but it is, since we've talked about displacement as the net area, it's just the change in position. That's what happens when we find an actual net area, the sum above and the, minus the below. If we want to talk about the distance traveled, we have to talk about just the actual area. So what's the area above the x-axis plus the area below the x-axis? So that's when we would have to look at like the absolute value. Because if we said, you know, what's the displacement here? Is 0. But, you know, again, if I walk from here to the podium and back, I know that distance is twice that distance, right? So then that's the displacement versus the distance traveled would look like this. Then since it's absolute value, this piece that's down here actually just gets reflected above like that. And so that would, you know, like whatever, that's the absolute value of velocity or whatever function we're talking about. Anyhow, not terribly important, but again, we can sort of put some of these mathematical ideas to in context of a physical idea. So that'll do it for 5.3. Do y'all have any questions on 5.3? All right, we'll take a break. 5.4 is very short. We're going to have to move through it pretty quickly because we still have 5.5 and 6.2 to talk about as well.
So I need to look the part.
You can say hi to him in person real quick.
I don't even know what questions.
Figure out what you want me to ask.
All right, let's start 5-4. We'll probably just do one example of each kind of topic here. It's called working with integrals. We're going to look at integrating even and odd functions and the average value of a function. So the first thing we're looking at is the even and odd stuff. And it's not that you necessarily have to do this. It's a whole lot more efficient if you can recognize when you can use this. So the idea is that if I integrate over a symmetric interval from negative a to positive a across an even or an odd function, we can simplify those computations. Specifically with even functions, if you'll notice that capital R is actually just doubled here. So instead of taking the integral from negative a to positive a, I can look at it half of it from 0 to a and then just double that result. And the reason that's easier is because one of our limits would be 0, and 0 is easy to work with, as opposed to like a negative 12 or whatever that happens to be. So I can take half of the region from 0 to a and double it for an even function. What happens if it's an odd function from negative a to a? What would that area be?
Your net area winds up being 0.
Yeah, the net area would just be 0. So that's super helpful. If you have this really complicated odd function that you're integrating from like negative 5 to positive 5, you really don't have to do anything because you know it's going to be 0. So that's what's presented here in this theorem. If you're not going to use these, I would definitely know what these are saying. We can still just default back to what's the antiderivative of f, what's that evaluated at a, and then what's that evaluated at negative a. But if you can utilize these, they're a lot more efficient in going through that process. Oftentimes it might not be like terribly straightforward whether a function is even or odd. So just as a reminder, an even function is one where f of negative x is equal to f of x. So in other words, replacing x with negative x doesn't actually change the function. Cosine is an even function. An odd function does anybody remember how to determine if it's an odd? If a given function is odd? Yeah. F of negative x is the opposite of f of x. Or, as it's less commonly seen, that the opposite of f of negative x is f of x. And so, in other words, if I replace y with negative y, and I replace x with negative x, and it's the same function, then you have symmetry with respect to the origin. So let's write this just as a reminder as well. Even functions are symmetric I'll just abbreviate, with respect to the y-axis, and odd functions are symmetric with respect to the origin. Sine is an odd function. Again, you don't have to use these necessarily. It's just a lot easier if you can. Move on. We're going to skip that one and do this one. Example 2. integral from negative pi over 3 to pi over 3. That's usually the indicator right there as to when these are used. If you're going from a negative value to the same positive value, that's when it's worthwhile to check for functions that are even and odd. So let's just split these up. I mean, we don't necessarily have to, but we can analyze each one of these functions individually. So we've got that one. We've got the force cosine x sine x, and force sine of x to the fifth. What did we say about cosine? Yeah, this is even. Cosine is even. What about sine? Sine is odd. So what would this last integral be? That whole thing is just 0. There's really nothing to do there, because this whole thing is 0. What about cosine times sine? Is that even or odd or neither? Yeah, so it's not clear. Since it's cosine of x times sine of x. So we'll just test that one out to see if it's even or odd or neither. Let's just kind of make some room here and say this is our function. The 4 doesn't matter, we can take it out of the integral. And then we'll just look at what is f of negative x. That's cosine of negative x times sine of negative x. Since cosine is even, what's the cosine of negative x? Cosine of x, right? So that's the same thing as just the cosine of x, because cosine is even. Since sine is odd, what's the sine of negative x? Negative, not negative x, negative sine of x. So cosine of negative x times sine of negative x is really cosine times negative sine, which is the negative of cosine times sine. So really what we're comparing f of negative x to f of x initially to say, well, is this cosine sine function even? Because f of x is not equal to f of negative x, right? So that tells us immediately that it's not an even function, since f of x does not equal to f of negative x. It's not even. Now the functions aren't like numbers in this sense. If you've got a number, it's either even or odd. But functions could be even, odd, or neither. So just because you say a function's not even doesn't necessarily make it odd. But what we do have is we have f of negative x, and if f of negative x is the same thing as the opposite of f of x, then the function's odd. So is this true? Is f of negative x the same thing as the negative of f of x? Yeah, because f of negative x is negative cosine times sine. We just computed that. And the opposite of f of x is just the opposite of our original function, cosine sine. It's the same thing, right? So f of x cosine times sine is odd. So that's super helpful because we don't know how to integrate cosine times sine right now. So it's just really convenient that it just goes away. So since that's an odd function, all of this is 0 as well. So really all we have to evaluate is this first piece. That's, since it's even, we're going to write it, we're going to half the interval from 0 to positive pi over 3, and then double the result. I would double that result. Now you could, of course, just evaluate it. What's the antiderivative of cosine 3x? Evaluate it at pi over 3 and then negative pi over 3, and get the same result. So it's not absolutely necessary, but here it's super efficient that we recognize those functions are odd, so we don't even have to deal with it. So then, what's the antiderivative of the cosine of 3x?
Oh.
Sine 3x over 3.
Yeah, sine of 3x over 3. Evaluated from 0 to pi over 3. So we'll just write that as 2/3 times the sine of 3x from 0 to pi over 3. And then we plug in our bounds. We have sine of 3 times pi over 3 minus the sine of 3 times 0. So you have the sine of, 2/3 times the sine of pi, which is 0, minus the sine of 0, which is 0. So that all of that stuff we started off with originally is just 0. Yep.
Where did that 2 come from that you put up?
Because what we did was we said instead of looking at cosine from negative pi over 3 to positive pi over 3, that we're just going to look at this right here and double it. So we looked from 0 to pi over 3, took that area, and then we doubled it to get this one.
Okay.
So that 2 is the doubling of that area. And again, it's not necessary to do that. It's just now that one of our bounds is 0, in theory, it should be easier to evaluate. All right, so I'm just going to write all that up here. Okay, any other questions on this? The next idea is the average value of a function. So if you think about, like, if I have a function, if this is my function f of x, and I want to know, like, maybe, I don't know, maybe that's a mountain ridge. On average, how tall is that mountain? Or on average, what value does this function take from A to B? There's infinitely many y values there, but we can actually say on average this is what the y values are. And so the way we can do that is we'll just put a whole lot of rectangles in there and say, well, the average value that we're calling f bar all I do is take the values in question. We'll say, let's say this, approximately. I say f of 1 plus f of 2 plus f of 3 plus f of 4, or however many rectangles I used, right? I'm adding up 4 things, and then I divide that through by 4. That's going to give me an approximation to the area, or to the average, rather. But in order to get the exact area, I need to add up infinitely many of those things.
So how far off would it be if you just evaluated it with like 3 values? So or I guess like 3 squares. The only reason I asked that is like because as horrible as it may sound, some tests will will have you evaluate stuff like this, but they give you the calculator, a calculator that's like a little worse than like the basic Windows calculator.
Like what kind of test? What do you mean?
Like PCATs and MCATs, like medical exams.
But they're giving you like a data set, right?
Not really.
No.
Because the whole point of those tests is not really to find the answer, it's to find an approximate answer, because they're all multiple choice. You never type in anything. So you find an approximate answer. It's like those tests are almost more how good you are at taking a test, not how much you know the material.
Of course.
All right, so like if it were to give you, if I remember I had some questions like that, and it essentially gave you like the A and the B, and then it gave you the line. But the calculator was like, a dollar store calculator. They give one to you. So I'd be like, I'd be curious to know like how far off would it be if you were to just evaluate, since you wouldn't have the ability to use any kind of summation or anything like that. How far off it'd be if you did it with like maybe 3 or 5 values. If you looked at the x star of k at 3 different values.
I think it would really depend on the function at that point.
Okay.
Yeah, I would have to see specifically what you're referring to.
Okay.
Yeah, but probably not good.
No. Okay.
Probably not good at all. So the idea is to use infinitely many of those rectangles. So if we looked at, we just chose specific values 1, 2, 3, and 4. But in general, if we said that it's f of x1 plus f of x2 plus all the way to f of x sub n, then we have to divide by n. Actually, this would still be approximation. We're using a finite number of rectangles. Even if that's 1,000,000, it's still an approximation, a better approximation. But in order to make this exact, we've got to look at the limit as n approaches infinity. It's just exact as n approaches infinity. So then the average value, and that's just some number, right? Just like your class average, it's just a number. Exactly is equal to the limit as n approaches infinity on this stuff here. And in order, just to make a little bit more sense out of this expression, notice this top part. That top part, written as shorthand, is just the sum from k equals 1 to n of f of x sub k. All right, we're just summing up y values up top. We're gonna rewrite n because n comes from the same arena that our Riemann sums came from, where we sliced it up and approximated those rectangles. So the idea that the number of rectangles is still related by, well, we should write it over here. delta x is b minus a over n. Remember that formula? That n is the same n as we have here because it's still the same, it's the number of rectangles. So I'm just going to rearrange this here. If delta x is b minus a over n, then we can solve for n and say that it's b minus a over delta x. So that's what we'll put here instead. This is b minus a over delta x. And so that kind of changes the way we're going to look at this, because then we're going to multiply by the reciprocal. That delta x comes up top to multiply the f of x sub k. So that delta x will come up here. And our b minus a will stay on the bottom. I'm sorry, sum from 1 to n. So what does the top part look like? This 1 over b minus a is just a constant. It's some number. It's not affected by the summation nor the limit. But what is the limit as n approaches infinity of this sum right here? The same thing as?
It would depend on the function, wouldn't it?
Yeah, it does. The value actually depends on the function, but we had another notation for the limit as n approaches infinity on the Riemann sum. It's super important.
Oh, is it the...
Fundamental theorem of calculus.
Right, yeah, that's the definite integral, right? So let's write this. It's still f bar, but all of this stuff, all of that stuff is just this thing. Sorry, remember that the integral sign from a to b, that's our shorthand notation for infinite sum. And then all of it is over b minus a. So we'll just take that constant out, 1 over b minus a times that. And that is our average value. That's our average value for a given function. Do we have the thing below, maybe? Yeah, okay, so it's down there if you could reference that. And so the way we can like visually interpret that is if we say, this f bar is just some y value. If we multiply both sides by b minus a to clear this fraction, then I think it's down here. Yeah. Then we have b minus a times the average value is equal to the integral. We know how to interpret the integral from a to b. That's just the net area under the function from a to b. But now we can say that this net area is the same thing as the average value times b minus a. If we take b minus a, it's just this length right here. So this is b minus a. The average value is just some y value. So this is f bar. Whatever this height is determined by f bar. So when we multiply f bar times b minus a, it just gives us the area of that rectangle. And what we're saying is that the area of this rectangle here, this area is the same thing as the area under the curve from a to b. So, this area is the same thing as the area of that larger rectangle. Oh, sorry, this is up here too. Let's see here if I can draw this. So that area is equal to that area. Where this length is b minus a and the height is f bar.
In that drawing, the F bar, that's like an accurate height
Yeah.
for the measurement. That's not, they're not using
Yeah.
that as like an approximation or anything.
Yeah, not an approximation.
Okay.
It is, so it's like if we looked at if we look at all of these y values from here to here, and we said, what are all of these y values? If I took all of those y values and then averaged them, we would say on average, they take that value right there. Or again, if that's a part of a mountain, what's the average elevation of this mountain? It's whatever that number is right there.
I'm assuming we don't need to know what that, like whether that's a set percentage or anything like that. F bar generally be
Just
either
some
given
number.
to you
Yeah.
or are we even gonna see something like that in a final?
No,
where
we'll just
F bar is
compute
gonna
it.
be- Okay.
It'll say, like for instance, our problems is, here's a function defined on an interval. What's the average value of that function? So, like let's look at this visually too. So all we're asking is, if we were able to look at every single y value here, from here to here, all of these y values, on average, what would they be? And then that's what we're actually going to compute with that formula. So it says we have to compute the average value. We have to compute 1 over b minus a. So again, that's just the interval here. This is A and this is B. So we have 1 over pi minus 0 times the integral from 0 to pi on this function. Okay, let's combine the constants, the 1 over pi and the pi over 4. So that we just have 1 over 4 integral from 0 to pi, sine of x dx. What's the antiderivative of sine? Negative cosine, evaluated from 0 to pi. And honestly, I would put that negative out front and multiply it in later. So we're putting that negative out here. Okay, so we've got a negative 1/4 times cosine evaluated at pi minus cosine evaluated at 0. Is everybody all right with what we've done? This is the average value that we're computing. So we have our negative 1/4, negative 1 cosine of pi, minus 1 for cosine of 0. So we've got a negative 1/4 times negative 2, which is positive 1/2. So on average, that function that we looked at just a minute ago, on average, the y values are 1/2. So there, the 1/2 is there in green. That's, on average, that's what all these y values are. But what we also said was that this average value from A to B so there's our interval from 0 to pi. There's our b minus a. The length of this is pi units. And we now know the height of that is 1/2, right? Because it goes up to our average value. This is f bar. So this dimension here is 1/2. So we're saying that the area of this rectangle generated by that, we're saying that the area of that rectangle is the area under this curve in the x-axis. So this rectangle, that area is equal to this area. Is another way to look at it. But in general, what we're saying is that on average, the y values that are taken on by that function from 0 to pi are 1/2. And maybe that makes total sense from the graph itself. You can see that it's from 0 to pi, that, you know, these y values up to this point here, and these y values after that point, they're all the same. It's a height of 1. Maybe intuitively you can think that on average the values would be 1/2. Okay, so that's average value. Do y'all have any questions on that? I think that's the end. That's all we're doing for 5-4. Really, outside of the antiderivative formulas from 4.9, the only technique that we get for finding an antiderivative is here in 5.5. So basically, if you're looking at an antiderivative and it's not one of those, it's not something you can simplify, then we've got one technique we could perhaps rely on to determine an antiderivative. And the substitution, think about the substitution rule as the reverse chain rule. And so what it says is, if we start off with this integral here, this one here would be on the left. That's typically, you know, of the form of an integral that's given to you. It says find this antiderivative. What we're going to do is we're going to make a substitution so that this, you know, a more complicated integral that we're trying to figure out via substitution gets translated into a lot more simple of an integral. The u being g of x is this inner function here. So that turns into this. This is an inner function. We're thinking of composition because that's our chain rule. So inner function whose derivative is present in the given integral. So that, at least initially, we'll see that in order to identify what our substitution should be, it's going to be this right here. We're going to look for a function whose derivative is also present in the integral, and then say, well, since that function and its derivative are present, that particular function is going to be what I substitute for. That's what we're going to let u equal. So it's, you know, like you've done substitution stuff before when you've seen things that are like quadratic in form. So like something like that, instead of like expanding it out, you could say, oh, that's quadratic in form. If I let u equal like 2x minus 1, then this is u squared minus u plus 5. And so that's quadratic. I factor it, u minus whatever, u plus, right? You've done this before, whatever that happens to be. It's kind of the same idea. We're going to take something a little bit more complicated via substitution and make it into something more simple. For example, find the antiderivative of 2 times the quantity 2x plus 1 to the 8th. So one option we have, which we probably would not want to do, is just to multiply this out, right? We could expand 2x plus 1 to the 8th and multiply itself 8 times, collect all the terms, and then just use the power rule. The other way to look at it is in light of what we have up here. We have a function composed with another function, and then the derivative of that inner function, if you will, also present in the integrand. So if we look at this like, okay, well, this is a function, you know, our outer function is raising it to the 8th power, the inner function is 2x plus 1. But more importantly, the 2x plus 1, that function's derivative is sitting right here. So this piece right here is like our f composed with g of x. And this piece right here is our g prime of x. Does that make sense? So f of x is to the 8th power, g of x is the 2x plus 1, and the derivative of g is right there. So as the theorem says, in order to find the antiderivative of this, what we're going to do is we're going to let our substitution, u, whatever you want to call it, we're going to let u be the inner function whose derivative is also present right here. So I'm going to say let u equal 2x plus 1. And just, if we piece this together, notice if we just make that substitution in that integral, then we're kind of in a bad spot, because we have this thing being u, but we've got to integrate that with respect to x. But if we're making a substitution, u or w or whatever, you have to then change the integral with respect to that particular variable. So if we just stopped there and said let u equal 2x plus 1 and tried to integrate this, it's not going to do anything for us. So when you're using the substitution method here with these antiderivatives, not only do you have to identify what function you're going to substitute for, but you also have to involve the derivative of that substitution. We can't account for this dx in terms of u unless we involve the derivative of our substitution. So the derivative of the substitution, the derivative of our function u with respect to x is 2. Does everybody agree with that? Or u prime is 2. And so to account for this dx, notice what we have left to account for in the original integral is this 2 that's hanging out and this dx that's hanging out. So if we take the derivative of our substitution and we rewrite that as du equals to 2 times dx, just multiplying through by dx. Now this 2 here times this dx here is just that du. So that's the integral of u to the 8th. So notice that outer function didn't get changed. It's still to the 8th power. And then our du takes care of the dx and the 2. So now we have an integral just in terms of u with respect to u. So really the key here is being able to identify what you should substitute, and you always end up taking the derivative of your substitution. Does anyone have any questions on that? So what is the antiderivative of u to the 8th with respect to u?
U to the 9th over 9.
Yeah, just the power rule, u to the 9th over 9 plus c. And then we resubstitute once we're done finding the antiderivative. So our u was 2x plus 1. And that's our answer. So of course we could check, right? Is the derivative of this thing in the box 2 times 2x plus 1 to the 8th power?
Yes.
Yes. All right. Are there any questions on this? That's pretty much the very basic type of u substitution that we can do. So if you're confused on what we've done or why we've done it, you've got to ask. It's just going to compound from here. And seeing a couple more might help. So looking at this integral here,
6x plus 1 is the derivative of 3x squared plus x.
yeah. And so that's where like, if you notice, your knowledge of derivatives actually does come back here. If we look at this 3x squared plus x and say, well, the derivative of that 3x squared plus x is sitting right here, that's 6x plus 1, that tells us that since this function on the inside of the other function, the square root, the derivative is present, that should be our u. So that's going to be our substitution. We're going to let u equal 3x squared plus x. Well, you'll end up putting it all together at the very end, but I just want to write this out as it would be all we've accounted for, we've got still the 6x plus 1 times the square root, that's u, and then this is still dx. So we still have to account for this 6x plus 1 and this dx in terms of u. And then that's where the derivative of u comes in place. So the derivative of u with respect to x is 6x plus 1 dx. Again, what we're really doing is computing this and then multiplying through by dx. So the derivative of our substitution, and then we multiply through by the dx. So we're just isolating the things that involve u and the things that involve x on different sides of the equation. Okay, so after we've substituted and taken the derivative, what is our final, our new integral in terms of u look like?
Antiderivative of square root of u times du.
Yeah. It's just the antiderivative of the square root of u times du. Let me write this here. Because this du accounts for the 6x plus 1 and the dx. Is everybody all right with that? Questions? Yeah.
Oh, never mind, actually.
So once again, it's now a power rule, the u to the 1/2, antiderivative of u to the 1/2. Two-thirds u to the 3/2 plus c, and then we resubstitute. That's our result. All right. So you're never going to integrate two different variables. If you're doing that, if you're at a point to where you're doing that, then you haven't substituted correctly, or you haven't taken your substitution far enough.
Say that again?
We'll never integrate with x's and u's together like that. If that's where you end up, then you know you've done something wrong or haven't taken it far enough. We're always going to integrate a variable with respect to that variable.
Does this rule apply if it's like a third derivative? Can that still work? Like if your u was like a f3 prime of the left side function, does this still
It could, like if it were like e to the x or e to the 2x or something like that.
Yeah, or like if your 6x plus 1 was the result of, say, whatever's in the square root function, the derivative of the derivative of the derivative. Like, you know what I mean? If you were to get that far
Yeah.
and then you finally find that, does it still work?
Not like for this one particularly, it wouldn't work because even if we had like 6 times the square root of 3x squared plus x instead of 6x plus 1, then a u substitution isn't going to work there.
No.
No,
Okay.
probably not. Because you're basically having to just do this thing with respect to x, and this the 6 is hanging out over here. So like, how would you do that? You could try to substitute, but the substitution there's nothing else to take care of, right?
Okay.
So your substitution would be still this right here. The derivative of your substitution would still be this right here. But the problem is that you don't have a 6x plus 1 hanging out.
But like if you wouldn't be able to say then look at the derivative of that, you find that it's 6, and then hey, what do you know, you got a 6 right there.
Oh, right,
It doesn't,
Yeah.
it won't work in that sense. This rule generally only applies to a first degree derivative.
Right, because if you take, like, if you took the derivative of your substitution again, if you took the derivative of your substitution again, this notation is kind of weird.
Like would it be du? Oh, okay, yeah, d
This
squared
right
u.
here.
Okay. Oh,
That would be 6, but you don't have a dx squared in your original integral that you could account for. So then, maybe your substitution after that ends up looking like this. And
Right.
now that's no longer a linear thing, like the length of a rectangle times the height.
Okay.
Sorry. D squared u. You don't want to do, like, we never would do that.
Okay.
I don't even know how you would do that. So it's always just the first derivative of your substitution, because that's what gets that dx in there that you have to account for in the original integral.
Okay.
Yeah, any other questions?
And this can only work when you have the derivative of the function.
Not quite. Usually that's the key indicator. What we'll see is as we look at different examples, it doesn't have to be like a one-for-one, like the exact derivative doesn't have to be present. It can be a constant multiple of your derivative, or something else. So even this process isn't as like straightforward as these first few examples would indicate. Let's see if we have a different example. So a couple of these ones from the table, like cosine 4x or cosine of ax, e to the ax, those antiderivatives are really computed using substitution. It's a lot more efficient to just know them, but like if we were going to substitute here, we would say, all right, well, I'm going to let u equal to 4x, and I realize at this point that the derivative of 4x is not present in that integral. But the fact of the matter is when you're doing u substitution and you're off by a constant, that's totally fine. Because what happens to this constant, we don't have a 4dx present in the original integral, so all we're going to do is just divide or multiply both sides by a fourth. So all I have to account for is that dx, right? There's not a 4dx in the integral. There's only a dx. So I'm just going to move the 4 to the other side as a 1/4. I'm going to use this and this for my substitution. So our 4x was u, and our dx became 1/4 du. Well, that 1/4 is a constant multiple, so we'll pull that out. Take out that 1/4. What's the antiderivative of cosine u with respect to u? Sine u plus c, and u was 4x. So what we have is the same thing as our table would indicate. 1 over a sine of ax. So all of those ones with the a's present, they're already a u substitution. You just don't have to u substitute if you remember that. So like this first one here, right? Like if this cosine of ax is the antiderivative is sine ax divided by a. It comes from the substitution.
Why did you get rid of the x on the du equals 4dx?
Oh, so we didn't end up working with this one here because the derivative of our substitution was 4dx, and we don't have a 4dx here. We just have the dx. So we're basically solving for what we had. We're solving for that dx. so that we can say that this dx right here is 1/4 du. And we can always do that if it's just a constant multiple times the derivative. You just move the constant to the other side. Does that, yeah.
So previously, we used to just solve for du. Why are we just solving for dx here?
Well, so because we don't have a 4 dx. The original integral wasn't 4 times cosine 4x dx, right? So when we said let's let our u be this 4x, the derivative of that gave us 4 dx, but we don't have that 4 in there to say that 4 times dx is du. But we have the dx present, so we just said, since we only have the dx, just solve for the dx to see what that is. It's 1/4 du. So that's the other two that we looked at. It just so happened that when we took the derivative, like it was already there multiplying dx in the original integral. So we didn't have to manipulate our substitution or the derivative at all.
On the exam, are you gonna ask specifically substitution? Like, if it was an example like that, we already know how to do that without the substitution.
Right, no, I wouldn't. The ones on the exam just say evaluate. Yeah, so if you do u substitution or you just know that it's 1/4 sine 4x, either one's fine. It's more efficient to know the ones from the table instead of u substituting for all of them. So you've got a similar thing here with e to the ax or e to the 7x. We're going to say u is 7x, and the derivative then is 7 dx. So the other way to think about it is well, I have a dx present, but I don't have 7 times dx. If I wanted that to fit exactly how this substitution's derivative shows, if I wanted to say, hey, wouldn't it be awesome if there were a 7 right there? Then I can do that as long as, because what I'm doing is I'm multiplying that thing by 7, but I can do that as long as I multiply by 1/7 as well. Does everybody agree with that? Because all I'm doing is multiplying this thing by 1. And then I can stop right there and say, well, hey, here's 7 dx. 7 dx is my du. Let me do this. My 7 dx is du. So that's for this piece I added in, and this dx, right? U is 7x, so that turns into e to the u. Remember, the outside function doesn't change. That's e to the 7x. That's e to the u. And then I still have this 1/7 hanging out times the antiderivative of that. So the only thing I accounted for was the 7x and the power of e as my u. I saw that the derivative was 7 dx. I didn't have a 7, but I put a 7 in there and multiplied it by 1/7. Is that okay? That way? I mean, it's the same thing you're doing when you do it the other way. Just look at it a bit differently. If you say u is 7x, then du is 7 dx. But I don't have a 7 dx here, so I solve for dx, and I say it's 1/7 du. So that this turns into the integral of e to the u times 1/7 du, which is the same thing as we have here. So some people like to do it the other way, where they add the constant in and then multiply by its reciprocal. That's totally fine, but either way you look at it, it's the same thing that you're doing. Do you have any questions? I would seriously recommend trying some of this homework, because it really, a lot of the stuff that we do going forward involves u substitution. And Calc 2, if you're starting Calc 2, it's all u substitution for a large portion of the first half. So try to do some of these homeworks just to see you know, what's going on. and
What's
we'll-
the
we'll
final
finish on
answer?
Thursday.
Oh, okay, we're not done with that
E to
one.
the 7x.
Yeah, we'll finish it on Thursday.
We'll finish it now.